this event. We are waiting for some of the participants in the workshop, so they're just getting done. So in 5 minutes we'll start.
Hello. Welcome all to IIT Indore. On behalf of the local organizing committee, we welcome you all in Indore. We hope that you have a nice session of the workshop today. Now we'll be having our first public lecture by Sri Kiran Kumar. Okay, so I hope everybody know him already. He will be giving his public lecture on space science missions of ISRO. Before we invite him on the stage, we'd like to introduce the speaker for today. Sri Kiran Kumar is Distinguished Scientist, Apex Committee, and has been Director of Space Applications Center, Ahmedabad. He assumed the office of Secretary, Department of Space, Chairman, Space Commission, and Chairman, ISRO on January 14, 2015. He's a highly accomplished space scientist and engineer with a distinguished career spanning over 4 decades in ISRO in the satellite payload and electro-optical imaging sensors for airborne, low Earth orbit, and geostationary orbit satellites, starting from Bhaskara TV payload to the Mars Orbiter mission payloads. There's various accolades attached to him. He led as a group director, principal investigator for Chandrayaan-1, an associate project director for Cartosat 2, deputy director, sensors development area for space application centers, group director, then later on associate director and director finally. And then finally he became the chairman ISRO. He is fellow of several national academies, sciences, Academy of Engineering, Remote Sensing Society, and various others. He has published about 76 research papers, 6 books, including monographs and many other journal articles. He's also recognized very much internationally. So we are grateful to have you, sir, and welcome you on the dais, please.
Good evening to all of you. At the outset, I would like to thank Astronomical Association of India, Astronomical Society of India, for giving me an opportunity to share with you what ISRO has done with respect to space science missions. So what I intend to do is, of course, just initially give you a little bit of what ISRO did in the initial period. Apart from what it is doing for space science, the prime activity of ISRO, of course, is for ensuring bringing use of space technology for development in the country. And space science activity itself, it started initially, as you can see, sounding rockets, bringing in the form of kits, getting it assembled in the church, what you are seeing, a dilapidated church there, and then the experiments being conducted at a place which happens to be the very close to geomagnetic equator, and if you conduct upper atmospheric research at that place, it will be beneficial for the entire scientific community, and it is under that specific, you can say, purpose this activity was started. And Tumba, we have the geomagnetic equator, and the sounding rockets went up initially from that place. So this is actually, you can also see the activity started in a very humble way with people carrying some of these rockets on cycles, etc. The first rocket went up way back in 1963, and then a series of our own sounding rockets for meteorological studies were done, and it was dedicated to UN on 2nd February, where this TERLS, what it was called, Tumba Equatorial Rocket Launching Site, for many of the developing country engineers and scientists, it was being provided as a facility. And in space science itself, when you look at, again starting from sounding rockets. Every opportunity that was available. Aryabhatta was the first satellite launched by India when Russians offered to take a satellite and then provided many of the component subsystems for that, and they launched it for us. And then SROS was our own Stretch Rohini series. So with every opportunity that was available for putting objects into space, India looked at how space science activities could be conducted, and we will see some of the details as we go down on this. Currently, of course, we have completed up to Chandrayaan-2, and Chandrayaan-3 is getting ready for a launch, and Aditya and Exposat. We will see some details in the coming slides. So this is how I said that the whole activity started. So we had a great visionary scientist, Dr. Vikram Sarabhai, who was looking at how this technology of space can be used for countries' development. And what he did at that time was, he convinced Americans that they should allow us to borrow their satellite, the advanced technology satellite they were building, ATSF, and it was moved over to the Indian longitude. For 1 year, India conducted an experiment, which was the world's largest socio-technological experiment of demonstrating how broadcasting from satellite can be used for reaching out to the entire country. You can imagine when the activities were started in the 60s, India was still struggling to meet the problems of, you can say, food, energy, many of these things, and communication was a big requirement. And this was the concept of using a satellite. Like today we are all familiar, direct-to-home television is with a small set-top box on our tables, and a television, we are able to see that. So at that time, the satellite was borrowed from Americans, but black and white television sets of ECIL and the front-end hardware, which is today a small set-top box, was earlier almost a half-rack set of equipment which was built in the country, and demonstrating to the powers that be that India can actually progress quickly both in broadcasting as well as communication if we make use of the space technology. And with that it went ahead. And then another very interesting story which I want to always tell is, when the activity was started, Dr. Sarabhai actually had to convince the fishermen in that region, you vacate this place for us, one day the country will benefit. And he had to make use of the services of this Bishop Peter Bernard Pereira for convincing the fishermen there. So what happened subsequently is, just as though to prove the point, from 1999 onwards, India was able to provide to the fishermen with a center in Hyderabad called Indian National Center for Ocean Information System. By looking at the color of the ocean in 8 different wavelengths, identifying the chlorophyll, through that the food chain of the fish, you can locate where the fish school is there in the ocean and give that information as prospective fishing zone to the fishermen. We have a 7,500 kilometer long coastline, and this information alone saves to the country almost 10 to 15,000 crores a year because of the petrol and diesel saved by the fisherman, because now he can go directly to the spot where he has to catch the fish. And then recently when we brought in the capability of our NAVIC, the activity is taken to another level, where a small battery operated gadget is fitted in the boat of the fisherman, and this gadget communicates with the NAVIC signals and then locates itself, and also a messaging system in the NAVIC gives to this small gadget latitude, longitude of the prospective fishing zone. A mobile in the hands of the fisherman does not know reading or writing, but in his mother tongue, through an app in the mobile, he is given in a video compass mode direction to the fishing point. And also you can realize that no mobile can communicate with terrestrial tower once you get a few miles into the ocean. So this mobile is simply a gadget with Bluetooth and Wi-Fi. It communicates with this battery operated thing fitted in the boat. So you can see here what was promised. A person who does not know reading or writing is able to make use of the most advanced technology of launch vehicles, satellite and application, and go through his livelihood. Not only that, he also gets information about weather vagaries in his mother tongue, and many of you would have been reading in papers our neighboring countries capture fishermen when they cross their international waters. So that alert also is given to him saying you are approaching the international water body, be careful. So you can see what was initially promised has been brought into operation. Today, state governments are buying a lot of these gadgets and providing to the fishermen across the country. And then another very important thing that happened is the ability to track cyclones and then predict cyclone landfall. And today, by virtue of this, the information about where in the coast the cyclone hits can be told with 20 to 30 kilometer location error and half an hour in time, days in advance. So disaster relief agencies are able to evacuate people and save them. So earlier super cyclones used to result in tens of thousands of lives being lost. But now, by virtue of all the activities that's happening through this space, this service is also available. So apart from that, there are a host of other things. But since today's topic is not that, I'll just stop there. That was just to give you a glimpse that how space technology was primarily aimed for providing solutions to the country. Then looking at space science mission itself, Aryabhata, which was the first satellite put into orbit by us, it carried an X-ray astronomy, aeronomy, and solar physics experiments. Of course, the satellite itself did not last for long because of certain problems, but then that was a starting point. Then there was a space lab based experiment which was called Anuradha, and then it was a cosmic ray experiment on the NASA's space shuttle, and this was a joint venture with PRL, ISRO, and TIFR. It provided the first unambiguous direct measurement of ionization states of individual nitrogen, oxygen, and neon ions of anomalous cosmic rays. Then as we started building our own launch vehicles, the Rohini satellite series was designed to be launched by our experimental satellite launch vehicles, and each of those satellites opportunity was used to put some experiments, like gamma ray burst experiment was developed, and it detected about 56 gamma ray bursts and provided time information, and also energy distribution of gamma ray burst photons. Similarly, there was a retarding potential analyzer developed by National Physics Laboratory, then which measured ionospheric parameters to study latitudinal variations, etc. And also many publications came out of this particular activity. Then if you look at in 96, again an Indian X-ray astronomy experiment which was conducted, it carried out observational studies of many bright X-ray binaries, and this was on our PSLV series of satellite. We were just graduating from satellite launch vehicle to polar satellite launch vehicle, and when these opportunities came, some of the satellites carried space science experiments. 3 identical pointed mode proportional counters were used on that. X-ray sky monitor was there, and this was developed by ISRO and TIFR together. And high background orbit, 2 to 3 months of observation time in a year, and about 20 X-ray sources got studied. It also resulted in a number of publications and doctoral thesis being done. Then by 2003, we were already getting into geostationary satellites in operation with our GSLVs, and this solar X-ray spectrometer SOX, it was called. It carried a high spectral and temporal resolution X-ray spectrometer between 4 keV to 10 MeV range, and again PRL, ISAC, and TIFR were the participating agencies, and a number of publications, and RT2 experiment on board a Russian Coronas photon satellite was also done. So one of the key things is all the opportunities that are available with collaboration or opportunities available as we were building our own launch vehicles were all being used for conducting these experiments. Then some dedicated science missions, the era started, and of course Chandrayaan-1 was the first of that, which happened in 2008, where there were about 6 payloads of other countries. Not only we were carrying payloads from our own institutions across the country, but we were also able to host a number of instruments from other countries on that. And of course, we are all quite familiar that this mission provided a significant international participation was there, and what it achieved, though man had landed on the moon and a large number of probes had gone onto the moon, etc., this satellite actually is credited with discovering the presence of hydroxyl and water molecules on the lunar surface. And before Chandrayaan-1 and after Chandrayaan-1, many perceptions about the moon got changed, which moon was considered dry earlier. And then, of course, after this demonstration, lot of data which was again looked back and then confirmation happened. Geologically dead billions of years back, but then dynamic and volcanically active. And then complete absorption of impinging solar wind protons by lunar regolith. Then after this, it is 20% of solar wind protons are reflected from lunar surface. So like this, it changed many of the perspectives about moon itself. So if you look at in terms of summary, more than 150 scientific publications happened. Water molecules in the lunar exposure and subsurface water ice deposits. Then it validates the lunar magma ocean hypothesis, and then reflection of solar wind, mini magnetosphere on moon, evidence of volcanic vent, lava pond and lava channels, riles, subsurfacially undamaged lava tube, etc. So, and also I will just quickly go through a couple of papers which came in different journals, geophysical research letters carried this. Then similarly, protons reflected from magnetic anomaly regions over the whole far side hemisphere, total deflection efficiency is about 1%. Over the anomaly regions alone, it's about 10%, and over strong anomalies as much as 50%. So this was one of the papers which got published. Then another observation of proton entry into near lunar plasma wake, magnetic field aligned flow. Similarly, discovery of a new population of suprathermal protons around moon. Many of these are work carried out by PRL and other scientists. First observation of transport of solar wind protons scattered from magnetic anomalies. Similarly, the current view of moon solar wind interpretation, Bharadwaj and et al. Have brought out in Advanced Geosciences. Then using ionosphere at the moon, also using radio occultation observations, a set of experiments were conducted, and this also got published in Geoscience Letters. So this was one of the interesting observations where there was a small segment where buried ryle is there, and which could actually serve as a potential site for future human habitat. Apart from Chandrayaan, then by 2011, there was an opportunity provided in YouthSat, which was a mini satellite, an Indo-Russian venture where solar radiation monitor and radio beacon for ionospheric tomography and limb viewing hyperspectral imager, these were done. Then of course the Mars mission. The Mars mission again was a very unique mission where India was the first country to do in its maiden attempt going around Mars. And then while initially it was expected that this mission would last for about 6 months, because of the launch capability we had, the mission itself survived till almost 7.5 years, and last year, after a long exposure to many eclipses, we lost communication with the satellite, and this a number of observations and whatever limitations that were there of taking this satellite into the Mars orbit, putting it into a highly elliptical orbit, was converted into some of the advantages for observation. So you could observe Phobos and Deimos. Of course, this is not so much relevant. In the Martian atmosphere, in the exosphere, results for MENCA, which showed first in situ composition measurements of Martian dusk sector. Then the MENCA observed suprathermal argon-40 in Mars exosphere, important clue to understand the energy budget of exosphere of Mars. So like this, many of the observations which could be taken from Mars, which lasted for almost 7.5 years, has provided significant inputs, and these are some of the images taken from that. You could see how the wind streaks are observed on that, and then superposing the images taken from Mars orbiter mission on other sets. And also, in fact, while the methane sensor itself could not do much with respect to actually observing anything related to methane, but in 1.65 micrometer range, it is the first global coverage of Mars. The reflectance and albedo studies could be done. And then the opportunity was also used for conducting radio occultation experiments when MOM signal is received on the Earth, passing through the solar coronal emissions, etc. And these experiments were conducted based on analysis of the data collected during the mission. And then, of course, measurement of the solar wind. So you can see some of the results which got published in MN Race in 2022, which shows on when they are at different distances with respect to the radius of sun, what kind of signals are present. Solar coronal turbulence near maximum phase of solar cycle 24. So this analysis of turbulence power spectrum, then at different heliocentric distances, what was happening, then many of the inferences, acceleration in the transition region. A lot of such studies could be done by Jane and team. And again, comparison of spectral index near solar coronal region as measured by previous spacecraft and spanning different solar cycles. Then, of course, we had the AstroSat mission, which is again a very unique mission, because this is a first, you can say, observatory class where the satellite was designed to provide observation and virgin data to our scientific research community, and it carried multi-wavelength in ultraviolet, visible, soft and hard X-ray observatory system. We have gone through more than 11 cycles, probably currently 12th and cycle is in progress. And then again, it has gone almost 7.5 years of operation. And many of the unique thing about this was all the payloads that were realized were developed in our academic institutions with the support of the space scientists and engineers from ISRO. And results have been extremely, you can say, gratifying, and you will be hearing a lot more. You have been hearing probably during the last many years of Astronomical Association conferences, etc. And it has done the discovery of extreme ultraviolet light from earliest galaxies. Then it's also shown thermonuclear X-ray burst in rapid succession, butterfly nebula. And then another thing that happened is you see CSAT imager studying about pulse phase resolved X-ray polarimetry, which is again a sort of a unique activity which was done. While initially when the instrument was built, the instrument builders did not have the idea that this kind of thing could be done, but based on a lot of subsequent studies, they're able to demonstrate the capability. And such an instrumentation for future is again under consideration for building and putting it into orbit. And this shows, of course, the far ultraviolet telescope. One of the unique things is it has got the highest angular resolution in the far ultraviolet, and also has got a sensitivity which is better than any other contemporary system on that. And then AstroSat, which is being used as a specific observatory mode where people can target it and then conduct studies. And then this also shows you, for example, gamma ray burst observation, what all has been done over a period. Then, of course, comes the Chandrayaan-2. What happened in Chandrayaan-2 is quite significant. In Chandrayaan-1, we carried some of the key instruments which were looking at what was happening, whether it was the mini-SAR or the hyperspectral imager, which were responsible for identifying the presence of water molecules, etc. So what was done in Chandrayaan-2, the instruments that were built with capabilities improved over corresponding instruments. See, the imaging spectrometer, infrared imaging spectrometer had a wavelength region which was going up to 5 microns, and synthetic aperture radar was a dual frequency SAR. So all the instruments in Chandrayaan-2 was built within the country, and then currently it has already provided almost more than 3 years of data, and one complete coverage of the moon using all this data is nearing completion. And once that happens, the satellite orbit probably will be brought down further, and you will be looking at providing information which is at much higher resolutions, etc. The orbiter itself is quite active, and all instruments are performing. And what problem came in that was only in the lander, and we did not succeed in our first attempt to actually touch down on with a very low velocity. So as a result of that, we crash landed on the moon. But then Chandrayaan-3 is getting ready, where the rover and the lander, after learning from the experience of Chandrayaan-1, Chandrayaan-2, it will get into operation, and large number of experiments, etc. are going on. So here the primary objective was to build all the payloads with capability better than what was there in Chandrayaan-1, and then as a result of that, do a systematic study of the entire surface of the moon and go further. So in that context, these were the three basic thematic investigations that were planned: water on the moon, IR reflectance spectroscopy, subsurface water in dual band L&SR, exospheric water chase, and then lunar composition in addition to class and XSM, then lunar topography, the terrain mapping camera, and also high resolution imager. So in a dual frequency SAR, like what I said, it is one of the very unique L and S band SAR operating on the moon, very close to the moon surface. It is there in 1.25 and 2.5 gigahertz operation. It is got full polarization and hybrid polarization modes operational, and this particular capability is the, you can say, forerunner for currently what you are listening to as NASA ISRO synthetic aperture radar, which is going up, which will be covering the Earth. It will be studying, and we have provided this L and S band aircraft version of the instrument for collecting, you can say, in situ data over North America and India using an instrument of this type. And of course, this just shows you the basic capability of the instrument. It operates with look angle between 10 to 35 degrees. It's about 20 kg total mass, power about 115 watts. These are some of the results which has come out from DFSAR with sensitivity towards lunar impact features, and then L-band SAR imaging subsurface impact melts. So many of these data is already published, and some more things are coming up in the current Planetary Science Congress that is going to happen. Then detection of water ice bearing regions using fully polarimetric dual frequency SAR. So a lot of work is going on in this area, particularly in the permanently shadowed regions where this becomes more meaningful. Then subsurface features of lunar craters, etc. By looking at the very high resolution images, both from our own sources as well as from the NASA's LRO, comparisons are being done. And this is an example of the kind of high resolution imaging that OHRC has got. It is one of the very high resolution imaging capability. Very small boulders, etc., or small objects also can be picked up using this. Of course, since the basic design was done for observing only close to perennially shadowed region, this data cannot be collected over high illumination regions. That's one of the limitations of this instrument, but it is used primarily for collecting information around the polar regions. This of course shows Vikram Sarabhai crater, one of the images picked up from TMC from Chandrayaan-2. And of course, imaging spectrometer, I said, this is an instrument which we have built where the wavelength goes, instead of 3 microns in Chandrayaan-1, it goes up to 5 microns. So as a result of that, its ability to do certain other activities in a more quantitative manner has improved, and a lot of results have come out of this particular instrument. And you can see that going up to 5 micron provides significant advantages. And you can see in this particular data set how between 2.53 and even beyond 3 you will be able to get data from the sensor. This is another activity which is going on, identifying unambiguous detection. And apart from this, of course, you also have the X-ray fluorescence instrument signature using class, which is again done a lot of very significant observations, and many new things are happening with that. Argon 40 distribution over the lunar exosphere, and the first global observation is happening on that. And then global map of argon 40 distribution, spatial heterogeneity of this. Similarly, sodium is also being mapped using this instrument. Some of the major results: magnesium, aluminum, silicon using XSM, etc. And then first detection of a large number of sub-A class microflares using XSM. And this is another, because sensitivity is very good, and because of that it's able to provide significant inputs. And then some of the results using the OHRC data is conducting distribution of boulders around the craters, and using that identifying the ages, etc. is also being done. And then you can see how the ortho image and the 3D perspective of a particular Dorsagai cave, what they call, using DM data as well as the hyperspectral imager data are being used for this. Hydration maps are being generated. So now coming to Chandrayaan-3, see the experiment, the two experiments which did not work in that was the lander, and obviously because of that lower could not be tested. But now the entire satellite is integrated and is going through tests, and even the platform which is actually designed for soft landing is getting verified using ground test facilities, which are maybe something like almost 100-meter crane and 300-meter type of cranes, etc. are being used, suspended objects, and many of these experiments which were not done in the first attempt, now they are going through all those tests. And then this time around, all the problems that were faced in Chandrayaan-2 mission is expected to be overcome. And when Chandrayaan-3 goes up, we expect it to be a safe landing, and then the entire capability of lander and rover should come into operation. So the satellite itself is now fully integrated, and it's going through certain environmental tests now. And then of course this is the APX getting integrated on that. There is also a thermal experiment which is called a thermal chest, and then this is a probe which will be inserted into the surface of the moon, and then making measurement up to 10 centimeter depth. Then another mission that is actually going now, recently probably you would have heard, and also there will be some presentation. VLC is actually been delivered by IAA to the satellite team, and now the integration with the satellite is in progress. And this mission is going to provide 24/7 observation capability of sun for coronagraph and many other experiments, hard X-rays, soft X-rays, UV imaging, charged particles, and then magnetic field measurements, etc. So uniqueness of this is CME dynamics, going very close to the sun, almost 0.05 radius beyond the sun's surface, and then providing information in the acceleration regimes, coronal magnetic field, spatially resolved solar disk in the near UV, onboard intelligence to detect CMEs, etc., flare observations, then solar wind, electrons, photons, and specific identified flags and count information through telemetry for high information. So then you also have multi-directional high cadence, both low and high energy, separated measurement, and the instruments that are expected on the in remote sensing. You have the VELC, which has been delivered already. SUIT is going through its final developmental tests. Then there is a Solex, then Helios, then you also have Aspects, and then plasma analyzer, advanced triaxial high resolution digital magnetometer. And then this shows just some of the images of the various payloads that are going to go on this. This of course shows you Swiss processing electronics and some of the just images for that. And there is also this Aspect flight models are all ready, and they are now sitting on the satellite. So another experiment that is going to be done probably later this year is the X-ray polarimetric satellite, XPOSat, which will be a satellite, dedicated satellite for polarization measurement in X-rays. And it's going to carry the polarimeter instrument and X-ray spectrometer. And then of course Disha and these two missions, of course, there is some changes taking place. Now the exact definition and then when it will go up, etc., are now going through another round of changes, because by the time originally it was conceived to now, a lot of changes are happening in the space program. So now the demand is the user community has to give more justification for the various payloads that are going to go up. So this will go through a series of further discussion before it gets into a specific operation. Then we are also in discussion with JAXA for a possible lunar program where India will be providing certain components in this satellite, and also certain observation capability. The mission itself will be a South Pole landing mission. Water ice and volatile investigation is the prime objective. And currently it is in the study phase, and if everything goes through, the launch is expected in 24-25. So in a nutshell, if you see, starting from Chandrayaan-1, which was the dedicated space mission, Mars orbiter mission, then AstroSat, Chandrayaan-2, now Chandrayaan-3 and XPOSat, Aditya, all are expected to be during some period in this year. And then Disha, H&L, of course, and Venus mission now have to get redefinition and reapprovals, etc. They have to go through, but that is the future. Okay, I think that in a nutshell is what I thought I would talk to you about and give you a glimpse of what has been happening in this area with respect to the space science mission. Thank you very much for a patient hearing.
Any questions from the audience? Do we have mics? Okay.
Thank you, sir, for this wonderful talk. Just want to know, we started with international advice and Russian support and so on. How self-reliant now in terms of the launch vehicles and programs that ISRO is conducting?
As far as launch vehicle is concerned, it's always self-reliant, so there is no problem. Launch vehicle, because of the nature of the activity itself, today what the government is trying to do is, by the time we build the capability, what we said, 4 launch vehicles with cryo engines, etc., the world has moved ahead, and now it has become more and more private entities are entering into the space, because space you can consider it as the 4th frontier now. and you have space tourism, space adventure, space habitation, everything. And a lot of private enterprise is getting into that, and they are building programs outside the space, means nation states. So as a result of that, India also is moving in that direction. So already you have seen a private entity putting their first stage early this year into that. Another company bringing in their own 3D printed engine, first of its kind in the world. So the India is actually moving ahead in providing a space technology capability to the country with both funding and resources coming from private entities, and government will continue to support both R&D activities, etc. In terms of launch vehicle and satellite, we are self-reliant, and we have also demonstrated that you can do things very differently from what others have done, but at the same time, whatever technology is accessible to you, you have used. What is not accessible, you have done indigenous development. Now, if you look at in terms of self-reliance in certain electronic components or certain specific things, that is a very different area where you still have to depend on availability of certain components. But we have, in many cases, overcome such problems also by adopting some alternate ways of dealing with. Just to give you an example, when the high-speed electronics availability became a question for our high-resolution imaging, we made use of a technique called the apparent velocity reduction technique, where electronics operating at a lower frequency can be used for high-resolution imaging. So in that sense, the ISRO's example has always been make use of the technology that is accessible to you and build things for solving problems you want to face. But in this, the real issue would be you cannot go too far ahead of the rest, but you can do things for solving your problems in a manner which is different and in a manner which consumes less monetary resources.
Thank you, sir. Also,
yeah, please.
Also, there are launches that ISRO made more than 100 satellites in one go. I mean, you have not, would you comment anything?
No, I'll tell you. See, while we built our capability, it was also an endeavor to make the best use of whatever capacity you have. See, obviously at that point in time, small satellite, mini satellites, etc., there was a large demand for launch. What happens is it's like you want to carry an envelope on a truck. So you have to wait for the truck to get filled so that the envelope goes along with that. Same way in launchers were being used for big satellites, and small satellite builders who were coming up with new ideas and new capabilities had to depend on big satellites being launched. So when we were building our launchers, we had many times excess capacity. So what we started, in fact, we started even ahead of others in terms of putting 10 satellites at a time, 20 satellites at a time, and 104 satellites when we launched in 2017. It was a record of sorts. And also, it is not a simple thing. You can imagine an object moving at 7.5 kilometers per second. You have to keep maneuvering and releasing objects from that every few tens of milliseconds, ensuring that they do not collide with each other with small velocity changes that happen. You need to do a lot of mission studies, a lot of analysis, etc. And also, the people who are going to put that in your launch vehicle should also have, actually, you can say, trust in you that you can do it. But because of the dual requirement of lack of opportunity for others to get it launched in a quick time, and we were ready to do a dynamic adjustment, we started that particular launch with a 68 satellites to be put in orbit. But between the time we started assembling to launch, we went up to 104. And such dynamic things does not happen globally. Not everybody is ready to take such changes in the mission and go ahead. So what ISRO did demonstrate is that while you build your capability, you can provide opportunities to others, etc. That's how almost 400 satellites we have launched for others, including what happened recently, this 36 satellites for OneWeb and Airtel. In fact, here also it's a very unique scenario. The satellites, a set of them were ready for launch in Russia. But the Russia-Ukraine war determined that they are not going to put it into orbit. So they were looking for alternate opportunity. So we were able to tweak our GSLV Mark III, and in its first attempt to put 36 satellites in the LEO orbit, one after the other, lot of mission changes had to be done. So both the company which was doing was ready to accept that risk, and we also had to take a risk, because the first time when you are trying, many changes which you do, whether it works or not, you have to have your fingers crossed. So the point what I'm trying to make is, it's a very dynamic scenario. Those who are ready to take risks will move ahead. Today, the country is now gearing up for enabling the entire entrepreneurship to get into the space which is expected to become $1 trillion in a couple of years. India should get at least 10 to 20% of that economy. That's the target. So that's where government is also making a significant amount of changes, making the facilities, whatever has been built, available to private enterprise because if they have to build those facilities for building their hardware, then the cost of doing that would be enormous. So ISRO means department is actually providing such facilities to the operators.
Anyone?
There's somebody there.
I have two questions. First one is how far we are in developing reusable rockets. Second question, any collaboration with ISRO is found to be extremely time consuming. I understand that this has been the case because of time scheduled activities of ISRO and not able to find time for other institutes as much as we expect it to happen. How do we address it?
Okay. See, you can see basically the issues were the primary objective of ISRO or Department of Space was to build the capability using space technology. And then what it can do depends on two prime things. One is how much resource is available for it to do the job, and also whatever R&D is required for ensuring that you remain contemporary. See, even while you are building a launch vehicle, what we have achieved today, if you compare with what others have done in LEO, etc., it's still not very comparable. But it was sufficient for doing a large number of activities. So the prime problem what we face is, if I were to tell you that the entire money that India has spent on space program, even after adjusting for the value of the money, is less than a fraction of what any superpower has spent in a year. So with the limited resource, what you can do has a limitation, and its manpower also is not infinite. And because of that, all the time, it was almost forced to make use of the industry. And if ISRO was able to actually nurture and develop industry, unlike many other organizations in the country, it was because of this requirement of limited manpower requiring to do the job. Now anyway, there are many problems of that type which result in what activities we can take up and do while performing the primary things. But then today the scenario is changing very much. Now everybody is in a flux. The department itself has to look at how it can cater to the new requirement of enabling the country to make use of the space technology, and then what activities department itself should be doing and how much support the government can give, both in terms of resources, etc. The government also has its problem. It cannot provide whatever we are asking. So all the time, because of the constraint, your developmental efforts gets affected. Like you are asking about reusable launch vehicle. See, if we have a solid motor-based first stage is not amenable for reuse. If you have a liquid stages, then they are amenable. So recently also we have done experiments where these liquid stages required to be throttled for operation. That means you should be able to change the thrust level of operation, so that after the preliminary takeoff, the stage, if it has to come back, then it has to operate at a very different thrust level, so that gradually you can reduce and then land. So these experiments have been done of throttling. Earlier, we also did reusable launch vehicle, touchdown demonstration. Many activities are going on, but all of that actually has to be balanced with the amount of resources you have and the amount of time we are able to provide to the people who are there. So it's a fine balance between available resource, money, and the time within which we have to do. For a country like ours, whatever capacity we have today, about 50 plus satellite, is nowhere sufficient. But then for having 3 to 4 times that number, you need capacity. For capacity, you need, again, investment and resources. So it's a big chain. So you have to view it in the context of everything.
Thank you, thank you. About second question, please address it about the collaboration and how fast we can move with ISRO. Okay, that has been very, very serious for institutes.
Yeah, no,
like
collaboration problem has been, like I said, is again linked with how much resources can be made available, both in terms of funding and in terms of manpower. But now the scenario is changing. So in the new in the context of new things happening, we have to work out and see how whatever problems that existed earlier in the area of collaborating and working with other institutions within the country can be changed. And then also probably the expectations of the other institutions on ISRO also has to change, because now the way department is going to operate is very different from what has been happening up to now.
Thank you very much.
Sir, I want to ask about what is the progress on cryogenic engines that we are developing?
See, we have 3 versions of the cryogenic engine which we are using and taking to geostationary transfer orbit, and also that is the one which will be used for manned mission. And then for the manned mission, in terms of building more robustness and then human rating, a large number of experiments also had to be done. All that has been completed, and now this year and early next year you will see a series of activities where the abort test and then unmanned missions, which will be done as precursors to manned missions, will all be happening. But in terms of cryogenic engine based launch vehicle, our Mark III, all the attempts so far has been quite successful, and we have been able to, and compared to our Mark II, it is much more, you can say, more robust, because the entire thing has been conceived and done here in the country. And then increasing the capacity in terms of the thrust level and also in terms of the efficiency of that, continuous efforts are going on. Recently, we had a series of tests conducted to increase the capacity of this cryo engine. So in terms of indigenous development, in fact, you will be happy to know that actual engines, etc., are all made in the industry and then integrated in the center. But otherwise, large number of fabrication, almost 80% of fabrication of rocket happens in Indian industry.
Last one, probably.
Hello, sir. Thank you for the talk. Sir, there is a great focus given by some other superpowers on telescope development, but we do not see much
On?
of telescope development, James Webb. So what is the plan for ISRO?
Yeah, again, I can say same thing probably at the cost of repeating. See, finally, if you look at India as a country, say, unless your economic strength increases, your affordability for a large number of activities depends on what money the government can make available. So without money, you cannot do things. And this is where, as the things are changing, as now we are the 5th largest economic power. So the ambition is to reach the top. And in a couple of years, we are expected to reach 3rd position. So as the capability of economic increases, your ability to provide more and more money for these programs also increases. But that is where the real task is. we need to be prepared for grabbing that opportunity at that time. So we need to do today preparatory things so that when we become when these things become affordable, we can do things very differently and then move ahead. So finally, it amounts to how much funding is to be possible for many activities.
Okay, thank you. So I would like to invite Professor Ajit Kembhavi to felicitate Sri Kiran Kumar. Before you leave, there is an announcement from the bus. Guys, the LOC has an announcement. Just stick around. Thank you, sir. Thank you, Professor Kembhavi. So I would like to, Suman, do you want to? Yeah.
So those of you who came from the city by buses, probably either you remember your bus number or the volunteer who came with you, right? So if you remember either of those two things, the buses are just on this side of the auditorium. Once you get out, there is a small pond with water lilies. The buses are around that location, and corresponding volunteers are standing in front of the respective bus. We would request you to take the same bus who is scattered around